Bismillahirrahmanirrahim. Assalamu alaikum. Let's continue with the same topic of PEC tower design. So today mainly we will be talking about in this section about the liquid hold up inside the PEC column, and then in continuation of this, I think by next lecture we will start with the calculation of diameter, pressure drop, flooding velocity, and then the last part of this design part, which is related to mass transfer efficiency. Actually these all parts are interlinked with each other, like the thing which we are going to discuss today, liquid hold up, that's necessary to be discussed before you start with the calculation of diameter or flooding velocity. Though today mainly discussion is related to liquid hold up, we will look what liquid hold up is, but during this discussion you will see that there are a few other parameters which will be discussed or which are part of the design of PEC tower when you go for designing such systems. Before I just start with this, I will quickly summarize the topic which we have discussed in the last lecture, that was related to calculation of height of bed mainly. So maybe in that lecture I was talking about height of PEC tower because one of the student has asked this question. So actually that height which we the formula we just studied yesterday and those equation, that height of the PEC tower mean actually we are talking about height of PEC bed inside the tower. Later when we will conclude with this discussion, whole discussion of the tower design, as we did it for the tray tower, you know that we added some space at the top of the trays as well as at the bottom of the trays, and those were needed for some specific reason. The same will happen here, because in PEC towers you know that we have to distribute the liquid, so there are liquid distributor at the top as well. Sometimes we need inside the beds, in between the beds, when bed height is greater than 6 meters, so in those cases you need it as well. There are gas redistributor, then like liquid collection and so on. So actual height of the tower is higher than the PEC bed, but the formula which you studied yesterday are those correlations equations, they are related to this calculation of the height of PEC bed. So in that we discussed that depended, or when we just simplified the formula, that depended on two parameters which were called as a number of transfer unit, NTU, that was just displayed with some symbol NOG, and then there was HOG, or that is called HTU, height of transfer unit. So both get multiplied and they give you height. So then HTU, that was simplest, that depended on 2-3 parameters, but then we said that NOG, that is a bit complex because that involves something called Weierstrass. So that need to be like and then that was, if you remember, that was something one correlation which was in the form of integral, and that need to be solved, and we studied that one of the scientists, they have provided this correlation related to NOG by solving the integral. And then few other correlation were these discussed for HOG and NOG based on the resistance, either it is on gas side, on liquid side, mean which one is dominant, as well based on the given data, if it is in the form of mole fraction, which we did all the equations, but if it is in the form of maybe pressure or concentration or any other mean related parameters or quantity, then how equations can be modified. So that's all about the things which we have discussed so far related to height. So actually from today the main topic is calculation of the diameter and this flooding velocity and all these parameters, but before that the thing which is liquid hold up is necessary to be discussed, because this highly affect the operation of the system or these columns. So let's talk about this, that what liquid hold up is and how it's get affected, and what are the important parameters or correlations from which we can calculate this liquid hold up, and then further can link it with the next calculations of diameter. When we look at these packed column, in packed column, in contrast to the tray towers, here you will see that actually inside the packed column there is a requirement of minimum liquid load, or minimum liquid flow rate should always be there. The reason is that actually, inside the packed towers, liquid flows on the surface of the packings, and on the surface of the packing, then liquid and vapor come in contact with each other. Actually, that liquid which is flowing on the surface of the packing, that makes the packing wet. So if like liquid flow rate is very low, and then it will lead actually to the liquid load at the same time to be low on the surface of the packing. So packing is not fully wetted, and when it is not wet, then the contact between the liquid and the vapors on the surface of the packing will be less, and that will definitely lead to the low efficiency of these towers. So packed tower will provide you like less efficient operation. So due to this reason, in order to maintain some specific flow rate of the liquid to keep the packing wetted, so we need to calculate that, so that then later on we can decide that what will be the diameter of the column to handle that amount of the liquid, so keeping all the other parameter like velocity as well pressure drop inside the design limits. So this lower capacity limit of liquid load, like the minimum requirement, so this is dependent on the packing, because when liquid flows on the surface of the packing, like it makes it wet, that is being called as a liquid load. So that is dependent on the packing type, the quantity of the packing supplements, and as well as the physical properties of the liquid. What does those mean? Like it will depend on the packing, which type of the packing you are using. As you have seen that there are a number of packings, and like there are random packing, there are structured packing, and they have different area available for the liquid or the gas to flow on their surface. Then there are the different type of material, like there are the metallic, ceramic based, or the plastic based. So all of those material will have different affinity actually with the liquid flowing on the surface. So as well, liquid physical properties, for example, we say that liquid viscosity, if it is like low or high, and it all affects actually the distribution of the liquid on the surface of any packing. So it's mean whenever we are looking for the liquid layout, we have to keep all these things in mind. So like here the diameter of the pack column, then definitely when we have decided that a minimum required liquid should be available there, it should make the surface of the packing wet. So you have to then design the column in such a way that its diameter should be such that it can handle that amount of the liquid. So diameter of the these packed tower is determined by the required maximum capacity, which is being handled inside any column to meet the specific separation requirements. So when we will be finding it, so then we have to find something called maximum allowable vapor rate as well. We will look in next few slides. Actually all these points are for your brainstorming, so that you can get the idea that liquid hold up is something which is important, and that is linked with the number of parameters. So it is also linked at the same time with the vapor flow rate, that it will also or affect the vapor flow rate inside the column. As well, when we have decided that we have to maintain some amount of the liquid inside the column for the specific separation, and we have decided the vapor flow rate, so that will be dependent or that will also affect the pressure drop as well as flooding inside the column. So all these conditions are linked with this. Up to here I have just introduced you with the topic that liquid hold up, why it is necessary to keep the like surface of the packing wet so that vapor liquid contact can be increased and you can achieve the desired separation. So that liquid hold up is linked with like diameter, vapor flow rate, pressure drop and flooding mainly, and this liquid hold up is dependent on the number of parameters which include like even liquid properties as well as the packing which you are using. So before we jump for studying then what liquid hold up is and how it is affecting all these parameters, let's look at few other facts that why it's important. So as you have seen yesterday, one equation for this height of transfer unit HTU, which was written in AR sometime also equal to HOG, if you remember from yesterday's lecture. So that was equal to, I think, V over here there was overall mass transfer coefficient on the vapor side, interfacial area, and then there was something this overall cross sectional area inside the tower, and that this V was the vapor flow rate. So it's mean here you can see that this HOG involves something called vapor flow rate. So overall when there will come the vapor flow rate, so this HTU, it is dependent on this the vapor flow rate. As well this K, calculation of mass transfer coefficient, these are, if you go back and look from where they come, so they involve some of the dimensionless numbers, and they are dependent as well on the velocities. So at the end of the day, this value of HTU, either it is like in the form of K value or directly K as well as the HOG, they are dependent on the velocities. So when something is dependent on the velocity inside the column, so it's mean velocity is actually dependent on something else, and that is like the flow rate as well as the diameter. You know the equation that volumetric flow rate is equal to area into the velocity. So it's mean if we are concerned about the velocity, actually velocity, how it is developed or how it will be varied, it depends on the two things, the flow rate of fluid which you are bringing in, either it is liquid or the vapor or the gas, which as well the diameter of the column, because based on that diameter you can find the area. And if you will change any of these, for example dia, it will change the velocity as well as if you change the flow rate, so that means this will be changing. So as we said already in the last slide that some sufficient liquid flow rate is mandatory for the good contact between the liquid and vapor and for the wetting of the surface of packing. So it's mean there it is dependent or affected. Actually velocity will vary, and we have to take care of this when we are designing this system. So this at the end of the day, the main parameter which is related to design, which is actually the column diameter. So this column diameter for any given system, so for design of a packed column, so it will depend on the number of things which are interlinked, and that is like the packing type, its properties like material, everything, and then there is loading, liquid hold up, flooding, and the pressure drop. So later on when we will conclude it in the next lecture, hopefully you will see that all these things are interlinked with each other and they will be affecting each other. So when you have to design, you have to take care of all these parameters. So in order to find something about the calculation of liquid hold up inside the column, because as we said that when we have to design the column diameter, so we have to start initially with the liquid hold up, and that is dependent on the liquid flow rate actually. So then these parameters also come inside like loading, flooding, pressure drop, and then finally we reach to the conclusion or calculation of the packing diameter. Some of the scientists Billet and his co-workers, they work a lot on this towards the calculation or towards the determination of liquid hold up inside the columns, and then their linkage next with the flooding velocity, pressure drop, and finally the conclusion or calculation of the diameter of the column. So here we are going to look at those correlation or the equation, but before that here something is important to mention. They have actually derived some correlations later in this part of the lecture we will look today. So that there will be something called A, that they said is A is the specific packing area. Later on we will see that this A will be appearing a lot, and this is one of the parameter which is like dependent on the, I think, type of like packing, different packing. They will be providing you this like different value of A, and that affects number of other parameters. So this a specific packing area, whenever we say specific, that's mean per unit something, and that is usually per unit volume. So here specific surface area is packing surface area per unit volume of the packed bed. So whenever you will look complete volume of a packed bed, and inside that how much surface area is being covered or provided by packing. So that is packing surface area. If you take one small packing and calculate its area, then multiply it with all those structure packed inside, for example 100 or 200 same elements are packed inside that beds, and overall you calculate overall volume of the packing and the surface area being provided by each of these packing. So this ratio and this is important to mention, because up to here in the last equation which we have seen, if you remember, for the rate of mass transfer in the two film theory, and later on the equation which we discussed, there was also this small a there, but a mean was like interfacial mass transfer area per unit volume of the packed bed. That A small which was being used in earlier equation, then there A stands for interfacial mass transfer area between the phases, like because in those cases you have to consider that area where liquid and vapor are specifically contacting and two film was being formed and mass transfer is taking place. So but here this is a bit different, small difference from that A. So but here they will definitely will be talking about somewhere interface area will appear. So in those equations where interfacial area will appear, that is represented with APH, interfacial mass transfer area between the liquid and the vapor phases, wherever it will appear. So before we just talk about that equation, let's look at something else. Before that, then we will come toward this, the calculation or the equation of the use for initially finding the liquid hold up. Before that, let's look what liquid hold up is and how it is dependent on some other parameters. So there is something here. I'm gonna show you few graphs. So in those there is parameter, those are plotted actually with this parameter superficial velocity and superficial velocity for both liquid and vapor. So what is superficial velocity? Maybe already you know that whenever something is flowing inside any pipe or any duct or from any path, wherever it is, and if only that phase is passing through the that path or that pipe, duct, anything through which it is passing, if that is only passing, and then the velocity of that fluid which is flowing through that path without any obstruction, without any like restriction in that path, that velocity will be named as superficial velocity. For example, this is one pipe and through this vapors are passing. Let's consider just instead of pipe we say that this is one column. Let's say it is later packed column, but initially we considered that this is totally empty, and any gas which we usually use to absorb some of the component of this gas inside the tower, let's consider that tower is totally empty, and when these gas will enter and pass through this column, and when leaves it will leave from the top. So if there is nothing else, no liquid flowing, no packing inside this, so the velocity of this fluid inside this column or inside this structure will be called as the superficial velocity. So simply you can say that this velocity is equal to volumetric flow rate, simply V is equal to velocity is equal to volumetric flow rate, let's represent it with the Q, and divided by cross sectional area of this total area through which is passing. So that is called superficial velocity. Similarly, let's say that if we want to look for the superficial velocity of the liquid, so then in that case we will again consider this complete column without the packing, without anything gas. So liquid will enter from the top, and when it will be leaving from the bottom, if we know its flow rate as well the area through which now it is passing completely, so the velocity it will be developing or it will be passing with is named as superficial velocity. So there is one example in your text simply for the calculation of superficial velocity for the liquid and vapor. Some flow rates are provided, and you can very easily do that calculation. Kindly just go through that. The formula is simple, that velocity superficial velocity, or simple, this velocity at the moment is equal to volumetric flow rate divided by the cross sectional area. So if I provide you that there is some column and it has some specific diameter, so with the help of that you can find this area, that will be equal to pi by 4 d square. So if you can find that flow area and as well as flow rate, I think in that example some flow rates are given to you. Actually they are molar flow rates, and then you can easily convert them to the volumetric flow rate if you have somehow molecular weight as well as the density. So just use directly from the given text and just do this calculation to find the superficial velocity for both liquid and vapor for that given case, so that you can more easily understand it. So let's look at this chart here. You can see that there is something called on this in this chart, if you see that this is about specific pressure drop. Here it is given, it's caption that specific pressure drop for dry and irrigated 25 mm. This is one kind of the Paul ring, so specific name for that is given. I can't just check from the text here, sorry, it is not showing completely its name. So overall in this diagram the data is given for the pressure drop, specific pressure drop. And what does specific pressure drop mean here? Again, as a few minutes back I told you that something specific when we say, so that's mean it will be involving divided by some dimension, like either it is sometime density per unit volume or per unit length. Here as it is shown that specific pressure drop is pressure drop and its unit are given here, meter of the water per meter of the packed height. First of all, here meter of the water, you know that you can represent the pressure in terms of millimeter of mercury. Similarly for feet of water maybe already you use, so meter of the water is unit for the pressure here, and per meter of the packed height. Well, it's mean that if you take somewhere some packing, and if we just consider the 1 meter of the packing height in terms of height, not diameter, in terms of height, if we take the packing and if any gas is just flowing through this packing, and if we can find the pressure drop and convert it in the meter of water, then just divide it per meter of the packed height, that will be giving us this specific pressure drop. On this y-axis this value is varying from here 0.003 to the 0.3. so this is a log plot for this, and here this is given. On the x-axis you can see that again log plot is here, and it is somehow specific gas velocity is given. Sorry, not specific, it is superficial gas velocity. As we have just seen what is superficial, so now you know that superficial is mean that if only gas was passing through the given column, and its unit are meter per second, here 0.0224 maximum value. And that actually the scientists which already mentioned, so they have developed a number of such data points and with the various packing with various systems, and then they reach to some of the correlation for liquid hold up. So this is also given by them, and in this case they used this some specific Paul ring 25 millimeter size packing, and this system in which it was used, that was air and water. Like in this column, when two fluids were contacting, liquid was the water and air was the gas, and pressure of the system was 1 bar as well as temperature was 20 degrees C, and other specs are also given. So diameter of the tower was 0.15 meter, height of the packing that was used here was 1.5 meter, and widage of or frictional widage inside this tower was 0.94. It's mean the packing which was used that was covering 6% of the tower, and 94% space is empty for flow of like liquid as well as gas through the tower. So when you look at these number of curves or the lines here, as I told you that on x-axis we have superficial gas velocity, on the y-axis you have specific pressure drop. So they are plotted along with third or other parameter, and which is here superficial velocity of the liquid, which is represented as UL and given in the meter per hour. So here when you see different lines, it's mean for each of these lines liquid velocity is different. For example, this initial one here totally straight line at which you can see the number 0, this is for like when there is no liquid, liquid like velocity is 0 meter per hour. It's mean this is dry packing, only there will be packing, and if only gas is just passing through, in that case it is. Then you start introducing the liquid. When you will introduce the liquid inside the column, so if you keep on increasing the flow rate of the liquid, so its velocity will just vary, because its already area is fixed, as you have seen that its diameter is given. So then these parameters are these number from 10, 20, 10, 40, 60 and 80, they are showing that liquid velocity is increasing inside the this column. So let's take some point from here. For example, if you see that initially when there is no liquid, like for the 0 meter per hour of the liquid flow rate, if you just look for the line which is shown here like straight line overall, you can see then it is just reaching here to the final point 4. So this is straight line, and on this line there are few points are shown. Actually those scientists developed or got some data from the experimentation, and then they have just drawn a trend line through those points. So here it shows that when on x-axis, when you keep on increasing the superficial gas velocity, what does this mean? It's mean when there is no liquid and gas is passing through the column, and with the passage of time what we are doing, we are increasing the flow rate of the gas. So when you will increase it, definitely velocity will increase. So when you are increasing it here, if I keep on moving along with this line at any velocity, if I will look, I will find here some pressure drop. For example, you take this point of 1 meter per second and just cross it, reach to this point when there is no liquid, you can see that there is some pressure drop up to here. You know that when the gas will be passing through the column and there is no liquid, still it will be coming in contact with the packing, so there will be some pressure drop when it will keep on moving. So if you just increase the velocity, there will be definitely no more restriction or more contact with the packing, and definitely the pressure drop will keep on increasing, but it remains straight. But when you look at some other points, as we introduce the liquid, just look for example again at this same point of 1 meter per second. So just look that when you introduce the liquid, and for the first line here 10 liquid velocity is 10 meter per hour, so you have introduced some liquid, and if you look at this point then and just match it with the like this 1 meter per second superficial gas velocity line, so I just observe that pressure drop has increased as compared to the initial condition of the dry system, when there was no liquid, pressure drop was less as compared to this case in which we just introduced some small amount of the liquid, and you have got the velocity of 10 meter per hour, and the pressure drop has increased as compared to the previous case. And then if you keep on observing and keep on going ahead, for example, we increase further the liquid velocity, and in order to increase that, as the dimensions are same, so you have to increase the flow rate of the liquid. So with this pressure drop will keep on just increasing. For example, I take this point of 60 line, so if I just connect it here, and you can see that's sufficiently high pressure drop as compared to the initial case is taking place per meter of the packed height. The reason here is that when gas is initially when we started with the dry packing, so there was just restriction to the flow of the gas, was only packing. But when you keep on flowing the liquid, so liquid will also be providing some resistance to the gas molecule, and due to this, pressure drop will keep on increasing inside the tower. So here you can just observe another trend. If you look at these lines which are for the liquid flow rate, initial is for the dry, that is totally straight line with, you can say, somehow overall pressure drop is changing. I can't say linearly because these are log plot, but that was like that remains straight. Still there will be pressure drop, but that follows some trend. But here in the other case, if you look for example, when you introduce the liquids, so for up to some point, for each of these lines, they are straight and they are just parallel to this line of the dry flow. But when you reach to some point, after that you can just see that there is a sharp increase in the pressure drop along the specific value of this superficial gas velocity. For example, if we take this line of 80 meter per hour, and if you just connect it with this, for example, 1 meter per second, just after this like if you just increase the velocity above this point, you can see that this gets more or less straight. So it's mean that pressure drop is highly increased after increasing the velocity after this point. And similarly, if you just come to the other line, after some point you will see there is a sharp increase in the pressure drop. So let's look at another graph that why it is happening, and then we will come back here. So this, in this diagram, you can see that that is also linked with somehow with the previous one. So then we will come back to the same point from where we are just discontinuing this discussion, that why this pressure drop has a highly increased after some specific point. So just look here. In this diagram, you are given data specific liquid hold up, as it was for the pressure drop, specific pressure drop. Like here there is a specific liquid hold up, that is liquid hold up. A specific liquid hold up mean definitely it is per unit volume of the packed bed. So it is the volume of the liquid on the surface of the packing per unit volume of the packed bed. So that is cubic meter per cubic meter. Its value is just ranging from here, like for example 1 into 10 raised power minus 2, and then you keep on increasing 2 into 10 raised power minus 2, 3, 4, and so on. So you will reach here up to 9 into 10 raised power minus 2, and then there will be something like 10 into 10 raised power minus 2, and that is written as 1 into 10 raised power minus 1. And then again after this 2 into 10 raised power minus 1, 3, and so on. So up to here 3 into 10 raised power minus 1, this data is given. So on the x-axis there is again superficial gas velocity in meter per second, as it was given in the previous case. Now while you can see here the other lines as they were in the previous case, they are for same like liquid superficial velocity, and that is in meter per hour as it was also in the previous case. So that is just there are a number of parameters given here with the like liquid velocities ranging from 2.8, 5, 10, and so on up to the 80 meter per hour. So there are different lines, and along the y-axis here we have like liquid hold up. and this also the data for the same system that like air water contact at 1 bar and 20 degrees C, and with the wide edge as well as diameter and tray height are the packed bed height are the same as it was in the previous case which we discussed. So it's mean anything in this column is actually observed, or these parameters are observed for the same column, so the parameters are linked with each other. So here if you see, you will observe that when you are increasing the superficial gas velocity, you can see totally horizontal lines, and on the y-axis, because we have like liquid hold up, it's mean for the case of any specific liquid flow rate which will be giving you the velocity or superficial liquid velocity. So when you just take for example any line, this 10, if I have 10 meter per hour, it's mean I am flowing the liquid at specific flow rate, and that finally give me the like 10 meter per hour velocity inside the column. So if I increase the superficial gas velocity through that column up to some specific limit, this liquid hold up remains same, like amount of the liquid throughout the tower on the surface of the trays, that remains constant. For any case you can take for the liquid flow rate up to some specific limit. For example, initially in this case it is up to even higher level, but in other cases it as you keep on increasing the liquid flow rate, then up to some value like lower than the previous one, you can achieve constant liquid hold up. So you see that when you reach to some specific point, after that these like lines get bent, and then you can see that there is a sharp increase in the value of the liquid hold up, because along the y-axis it increases. Let's take this value of like for example 40 meter per hour liquid like superficial velocity. So in this case, when there is a liquid velocity 40 meter per hour, in that case what is value of liquid hold up? Let's look at this cross here at some point, which is 8, so that is 8 into 10 raised to power minus 2, because it started here from 1 into 10 raised to minus 2, so its value is 8 into 10 raised to minus 2, and that you can say it is 0.08 cubic meter per cubic meter of the packed bed height. So that means that when you are saying it is liquid amount is 0.08 cubic meter per cubic meter of the packing height, it's mean for each 1 cubic meter of the packing packed volume, there is a 0.08 cubic meter of the liquid on the surface of those packing. That means like 8% area of that is covered with the liquid, the free area on the surface of the packing. As we said that there is a 96% free space between the packings available, so it's mean 8% of that is covered with the liquid in that case. So here you see that this liquid hold up, when you keep on moving along this x-axis, and along x-axis we are increasing the gas velocity. If you keep on increasing it, you can see that it remains constant liquid hold up. Its value will remain like this, 0.08 cubic meter per cubic meter up to some specific point, and after that point then it keep on increasing and finally increase too much, or exponentially somehow. So here then you can observe that in all of these cases that there is some dotted line, and he is calling it as a loading line. So this is the point up to where the maximum superficial gas velocity can be achieved, and without disturbing the liquid hold up on the surface of the packing. But when we just jump or cross this point, if for example the case which we took like 40 meter per hour for the liquid, and if it was just you were moving along this line, you can observe that somehow up to 1 or 1.1, you can say like up to here, somehow if you keep on increasing the gas velocity, keeping the liquid flow rate same, the liquid hold up is constant throughout the tower. But if you just jump, you keep on increasing the vapor flow rate, when you will just jump this point of 1.1, you will see the sharp increase in the liquid hold up. What does this mean? As we just keep on increasing the amount of vapor or the gas which is entering from the bottom of the tower. So when liquid is coming from the top of the tower, there is a packing, for example, inside this, and a liquid is just moving on the surface of packing. Vapor, liquid are coming in contact with each other, gas is moving towards the top and liquid is going down. So there is no issue, there is a proper distribution of the liquid inside the column. But if you keep on increasing the vapor velocity, so how you are increasing? Actually, you are increasing the vapor flow. When vapor flow is increasing, its area is constant, so it's mean then velocity will keep on increasing. So when velocity will keep on increasing, then you will reach to some point where the vapor flow rate is very high, and it will develop the condition same as you have already seen in case of the tray tower, that these vapor will start carrying the liquid towards the top of the column. And when they will start carrying the liquid towards the top of the column, so then there will be flooding of the liquid inside the upper side of the column. And when there is a flooding inside the column, so it's mean there is a liquid hold up that has sufficiently increased inside the tower towards the top of the tower. And when there is a high liquid hold up, that is shown here along with this, that when you will reach to the sufficient value, if you just go beyond that value, the vapor has now such high drag force on the liquid that they can hold the liquid up and they can entrain the liquid droplets towards the top of the column. And in that case, then liquid hold up increase. You see that when there is now more liquid that is covering the free space between the packings at the top of the column, so it's mean there are no free spaces, much more free spaces inside the column, as initially, for example, its value was 0.08 meter cube per cubic meter per cubic meter of the packing. When it is increasing, for example, you reach to this value of 2 into 10 to the power, like for example -1, it's mean liquid hold up has increased inside the column. And when there is more liquid, definitely it will be providing more resistance to the vapor of the gas to pass through. Due to this reason, when there is a more resistance for the gas or the vapors to pass through this, then there will be more pressure drop. And then now you can come back to this point, that as you keep on increasing the velocity of the gas and keeping the liquid value or like liquid flow rate same, for example, we discuss here the case of 40 meter per hour. So here you can check same for 40 meter per hour. If you just check that when you just increased this line of 40 with these like crosses, so when you just jump above 1, like for example here more or less the case of 1.1, here again you can see that for the case of more or less 1.1, you can see sufficiently high pressure drop. Up to here it was like straight line, but after this it has increased exponentially. So in that case, when liquid you just reach this limit of the loading line was the point, or loading point was that point on which up to where the liquid hold up is not affected by the superficial gas velocity. But when you just jump after this point, then that is affected and liquid hold up start increasing inside the column, and due to that then there will be high pressure drop inside the column. So from all this discussion, what you can conclude, you can see that liquid like hold up inside the column and or liquid traveling inside the column on the surface of the packing, that is not affected by the vapor flow rate up to some limit. But after you just reach that limit or you cross that limit, then you can see then there are a lot of problem inside the column operation, like there is a flooding, you keep on increasing the liquid hold, you keep on holding the liquid inside the column, and when there is more liquid accumulated at the top of the column, definitely liquid should move downward, but it is being accumulated at the top. At the same time, it will increase the pressure drop inside the column, and this will lead to disruption of the process. So due to this reason, all these parameters are linked with each other, and we have to take care of those, that our column should operate below these lines, which are like loading line or loading point, as well as the flooding point or flooding line. So in this diagram you can see that as we said that we keep on increasing the superficial gas velocity, you reach to some point which was called loading line, and from this liquid hold up can start increasing, and then finally you reach to some limit which was called flooding line. So whenever you look at these for any of these packing, so this loading point is more or less you have already close to like flooding point with the difference of only 30%. So still 30% increase in the velocity after this loading point will lead to the flooding point. Later we will just see now a few more points related to this. So there I will explain that then where we should operate our column, or what should be the velocity inside the column. All this discussion was with the superficial gas velocity. Maybe you will be thinking that inside the column I am talking about that there is a packing liquid is there, as well as the vapors are passing through, and but do you think that initially as we defined the superficial velocity, that superficial velocity was that velocity when there is nothing else, only one fluid is passing through the column, and that column even did not contain any packing as well as the liquid. So what happens, what do you think that what will be the effect on actual velocity if you fill the column with the packing as well as the liquid start passing through the column? So definitely the answer will be velocity will increase. The reason is for example, we calculate the velocity, that is like flow rate divided by the cross sectional area or area for the flow. So here initially there was nothing, only liquid was flowing, and we have calculated some velocity, and that was called superficial velocity. So now when you will introduce the packing inside the column, the flow area will reduce this area required for the flow, because now there are the packing, and through that there will be some area which I already told you here. If we take this specific packing that has a weightage of weightage fraction of like 0.94, it's mean 6% area is covered with this as well. Then later we discuss this case that when you introduce the liquid, so liquid also cover some area. For example, in this case, as I told you that this specific value at specific flow rate, that was 0.08 cubic meter per cubic meter, and that means that 8% area of the packing or on the surface of packing is covered with the liquid. So initially it was like already from 100%, 6% was covered with the packing, and now 8% is covered with the liquid. So then other area, I think 8 plus 6, 14. So if you just subtract 100 minus 14, 86% area will be available for the vapor or the gas to pass through in this specific case. So it's mean then when the area has reduced like from 100% to the like now 80%, so 86%, so in that case this velocity will further increase. So it's mean actual the velocities are higher than the superficial velocities are based on all this discussion which we just did. It's mean the actual velocity for any point inside the column will be higher than this superficial gas velocity. So it's mean for example, when we said that in this specific case of 40 meter per hour, the flooding or this loading line or loading point is approached when your velocity of the gas is 1.1 meter, but in reality this point will be reached even earlier than this, because in that case the velocity will be even higher than this point, and that can lead to this flooding. From these figures actually I have explained you all those things which are just summarized here. I will quickly go through. So if from the initial figure you have seen that when you increase the liquid flow rate, so gas phase pressure drop will keep on increasing for the given velocity. For example, I discussed this case that if you take this gas velocity of 1 meter per second, initially we started with this dry, and when we keep on increasing it, you can see that pressure drop was increasing for all these cases. So that is same mentioned here. So but up to some specific limit, up to some specific limiting velocity, these curve for each liquid velocity line, they were straight and parallel to the dry. for the pressure drop curve. But after that specific point, we have seen that then they become like there is a sharp increase in the value of pressure drop, and I have explained to you. So same is mentioned here, and that the reason was that after this specific point, as we have linked with this diagram, that liquid hold up start inside the packing, and then that leads to more pressure drop inside the column. So in this region, actually the region of constant liquid velocity lines in the figure 6.34, which are compared with the other figure 6.35. so in that case, specific liquid hold up and that is liquid hold up per unit volume of the bed, that also remains constant up to these specific points, and those specific points are up to where their pressure drop is also like straight line. But after this point, like here, liquid hold up is increasing and then pressure is increasing. The same was explained, mentioned here. So as also we took this point of 40 meter per hour for the figure 6.35, and same is mentioned that what is liquid hold up, that's mean 8% of the packed volume is covered with the liquid. So in that case, up to the superficial velocity of 1 meter per second, the operation is stable. But when you just jump above this point, then liquid hold up start increasing. So here the same is mentioned that actually in that case, when you introduce the packing, so along with the liquid also coming inside the column, so actually flow area for the gas, that is reduced. For example, I have told you already that it will become 86% in that specific case. So this is not necessary always to be 86%. For example, if you take any other high liquid flow rate, it's mean more area is covered or more volume of the liquid inside the column, so it's mean there will be still even less space than this 86%. As well, it depends on the packings, because initially when we studied the different types of packing, you remember that some packings are more like solidified, and there is less area available for the like flow, and in some are more open and there is more space for the flow. So it all depends or will vary. So upper superficial velocity up to where it does not affect the liquid hold up was called as a loading point, which we have seen with the dotted line, that was called loading line. So on any line it will be called as a loading point. So below this loading point, the gas phase is the continuous phase, and liquid it will not affect actually the liquid, and liquid will be just trickling down over the surface of the packing without being influenced, and there will be no problem. But the liquid hold up here only depends on the liquid flow, as you have already seen that when you will keep on increasing the liquid flow rate, liquid hold up will keep on increasing in figure 6.35. But above this loading point, definitely then gas begins to hinder the downward flow of the liquid, and we already discussed then the liquid will start holding up or building on in the upper part of the column. So if we keep on further increasing the gas velocity, we have seen that will reach to some point where there is a continuous liquid along the top of the packing, and column will reach to the flooding point. So flooding point is that point at which actually gas drag force is sufficient to entrain all the liquid in the upper part of the column, and it will not be flowing down the column. So definitely no more interaction between vapor and liquid, and no good separation at that point. So in the loading region, usually as already I mentioned this point, that actually when you are in the at the loading point, actually at the loading point already column operation is unstable, because gas has already starting entraining the liquid and starting dragging the liquid towards the top of the column. So at that point, actually superficial velocity at the loading point for any of the given curve is approximately 70% of the flooding point. You are already up to the 70%, and further 30% increase you will reach to the flooding point. So it's mean so that any column our PEG column should be operated below these points for the stable operation. So although we can operate the like column in a loading up to the loading region, but that will definitely not be good. So they are operated below the preloading region. Why it will not be good, I have already told. Liquid velocity vapor velocity to such point that it will start entraining the liquid in the upper part of the column, and then that will further lead to the like flooding inside the column, and pressure drop will increase, and like operation will not be okay. Up to here we have discussed about what liquid holdup is and how it is being affected with the vapor or the liquid flow rate. So this all the discussion or the diagrams, as I already said, that they were providing by some of the scientists. So finally they just after collecting the data and analyzing the various system, they have given us some expression to calculate the liquid holdup or the amount for this liquid to hold on the surface of the packing for the for those cases where it is like stable operation. So let's look at those correlations. So here they analyzed number of like systems, and they collected 3500 data points. As you have seen for various all of these curve which we have seen, that there were some point, actually the dots or the points, they are data points. So they develop like in a preloading region, like for this Bellet and his colleagues. So they have developed the dimensionless expression for the liquid holdup in the preloading region after analyzing some 3500 data points for 50 different test system and 70 type of like random and structured packing. And what they concluded after analyzing all these data, that like liquid holdup that depends on the packing characteristic, as well as it is dependent on the liquid velocity, density and superficial velocity, but not dependent on the superficial gas velocity. Due to this reason, in the figure 6.35 you have seen that in a preloading region, but this is valid for the preloading region, above preloading region, then definitely this superficial gas velocity it affects the liquid holdup, and that is the region actually that is not stable operation. Due to this, we are saying that in the stable region there were just straight lines with the increase in the like vapor velocity, so there was no effect on the liquid holdup. So you can see here the equation which is, or the expression this based on this experimental data. So this correlation is for calculating the liquid holdup. So liquid holdup, its unit were cubic meter of the liquid per cubic meter of the packing. So that is equal to 12 multiplied by some Faraday number and Reynolds number, their power 1/3, and there is a ratio between two areas, AH hydraulic area I think, and A that was specific packing area, and this is specific hydraulic area to this power. So then what is Reynolds number here? You know that Reynolds number is equal to diameter and velocity density over viscosity. So that is ratio between interfacial forces to the viscous forces, and they have developed this relationship in the form of a specific packing area. So that was because its unit, as already told you, that is area per cubic or per unit volume of the packing. So that will finally give you the like dimension of per unit length. So that can go back to the like this numerator, and it will give you the same dimension as you have generally for the Reynolds number. So here like this is expression for this specific case. You know that we can write number of depending on the situation for Reynolds number of the equations or the expression. So here this is also dimensionless, you can check for this if you wanna. So then there is Faraday number, and that is the ratio between inertial forces to the gravitational forces. Here it is viscous forces. So that is also like to use square of velocity of the liquid divided by gravitational expression, and this is specific packing area. So A is specific packing area, and that is packing surface area per unit volume of the packing bed, and this is the parameter which is dependent on the packing type, its material, and those things. So we will just look at later on at the end of the lecture at few table from where you can get some of the parameter they are given for the different packing. So from there you can directly take the value of A if you know their packing material and its size and so on. So AH is the specific hydraulic area of the packing. So I think you already are aware about the hydraulic radius that is used for denoting or representation of those objects which are not cylindrical. For those we use some terminology to represent their diameter or the radius called hydraulic radius. So this area which is hydraulic area is area based on hydraulic diameter. That is specific hydraulic area of packing. So hydraulic area per unit volume of the packed bed. So this AH over A is they have already also provided some correlation for these AH over A. So if Reynolds number value is less than or greater than 5, so initially if it is less than 5, so AH over A is calculated from this correlation, which is CH some constant dependent on the packing. So then there is Reynolds number and Faraday number, and if it is like Reynolds number is greater than 5, so in those cases then AH over A, like specific hydraulic area to the specific packing area, is calculated with the other correlation. So in your textbook table 6.6 actually lists number of the parameters related to different packing like random packing and structured packing. So we will just look at those. You can just directly find from the tables and can use it for the calculation. So various packing will also have the different wide fraction value of A, CH and some other parameters. This is the main correlation which can be used for calculating the liquid hold up, and later in next calculations in the next lecture, so we will be using it. Next few points here, just I am concluding it. Liquid hold up. So at low liquid velocities, like suppose liquid velocity low, it's mean if keeping the overall diameter of the one column same. So if liquid flow rate is low, so there will be low liquid velocity. So in that case liquid hold up is low, and the possibility is the sum of the packing will be dry, or there will be something like channeling and so on. So in those cases, like for low, you will get definitely the low efficiency, because when there is a dry packing, so there is no contact of vapor and liquid, and in that case for there will be low efficiency in terms of separation. So in those cases we need somehow more liquid distributor and redistributor, and so that we can achieve adequate wetting to achieve the specific superficial liquid velocity, and as well the wetting, so that can lead to the required separation. So in those cases, there are few other observation by those scientists that depending on the packing material, your liquid minimum superficial velocity should be for various material it should not be less than this, or it should exceed the given values. For example, for ceramic, if you are using, in that case the liquid velocity should be minimum, this is the value 0.00015, otherwise it should be above this. Then you will be reaching to the proper wetting of the packing inside any column. So that's it related to the calculation of liquid hold up by using this equation. If you are given the data for various packing, so you can find the liquid hold up, and example 6.15 describe this or is the use of this equation. Kindly just solve that example after going through this. Before I just finish it, I will just go to your textbook to show you the table 6.6 related to various properties of these packing. So here this is the table 6.6 characteristics of the packing. So you can see that there are the different packings. Initially they started with the random packing, and later you will see this is a huge table in which then there are structured packing. So inside this random packing, then you can see there is a packing material. We know that packing can be ceramic, metallic or plastic. As well, there can be different sizes of the packing or specifications. Then there is something, this factor FP, we will be using it in next lecture, that is called packing factor. So FP, then there is that specific packing area, which I told you that it represented with small a, and it is dependent on the packing type. It will be different for the different packing, and it will also if you keep same packing but material change, these values you can see that all they will be changing. Then there is wide fraction, this cubic meter per cubic meter of the pack bed. So that is also different for different packing. Initial versions of the packing were more solid and less area available for the liquid and vapor flow rate, but later they were developed with the more openings. Then there are few other parameters related to the packing which will be used also in the next 1-2 lectures related to those. They can also be, these are different constants which you can see from here, from this table, and they are given for both structured as well as for the random packing. Later on, being design engineer, for example, you have to present some solution for some specific separation, so you can select either random packing or structured packing, and then you can compare number of the parameters, for example the requirement of the diameter, as well pressure drop inside the tower and so on, and then you can select one specific solution which is good or suitable. So thank you so much. We will continue with the next stuff of like calculation of the diameter and pressure drop in next lecture, and hopefully by next lecture inshallah we will just end this design of the pack tower. See you. Allah Hafiz.